Yeah, I think we can start. So let me share my screen and we can start. Yeah, so can you see my screen? Hello?
Yeah,
Yeah,
yeah, it's visible.
yeah, okay. Yeah, so I'm Bhargav. I'm a PhD student in IISc, and every week from 4 to 5 p.m. on I Saturdays I take problem solving sessions for this course. So we'll solve some problems, and if you have any questions, just interrupt me and ask. Unmute yourself and ask me the question. That would be preferable to writing it in the chat because I can't always see the chat if I am like presenting my screen. Okay. So let's start by first recalling what we saw in this week. So in this week we saw the notion of p space completeness, and this is where the notion of p space completeness is similar to the notion of NP completeness, and it's defined as follows. So a language A in p space is said to be p space complete if for all languages B in p space B reduces to A in poly time. So basically if you can solve A in polynomial time, then you can also solve every language in p space in polynomial time, and therefore like p space complete languages are sort of the hardest languages in the class p space. An example of a p space complete language is a language of true fully quantified Boolean formulas, or the language TQBF. So a fully quantified Boolean formula looks like as shown over here. So here psi is an unquantified Boolean formula, and q1, q2 up to qn are quantifiers. So for example, here's what a fully quantified Boolean formula and two variables can look like. There exists x1 for all x2, x1 and x2, or x1 and x2 complement. So this is what a truly quantified Boolean, this is what a fully quantified Boolean formula is, and the language TQBF is the class of all is the set of all fully quantified Boolean formulas that are true. And this is a well-known p-space complete language. You would have seen the proof that this is p-space complete in the class. There are also some other p-space complete languages. Yeah,
Excuse me.
yeah.
In P space, B is reducible to A in polynomial time. So why do we take this polynomial time instead of maybe log space?
Okay, so when you define a reduction, you have something in mind, right? For example, when we define the polynomial time reduction from for p and np, we had some question in mind, right? Whether p is equal to np or not, right?
Yeah.
Similarly, while defining polynomial time reductions, the reduction that we have in mind is okay. So the question that over here that we have in mind is a p versus p space question. So if you want to talk about the L versus p space question, then you can as well define use log space reductions over here. So whenever you define the notion of completeness, you have some underlying complexity theory question in mind, and depending on that question you would define the reduction. So is this fine?
Yeah. Thank you.
Yeah. So then you would have seen the space hierarchy theorem, and this theorem is the sort of the space analog of the time hierarchy theorem, and it says that the class D space Fn is strictly contained in the class D space Gn if Fn is small o of Gn. So for example, this says that D space n is strictly contained in D space n square. So if you allow more space, you can solve more problems. Then you would have seen Lardner's theorem, which says that if p not equals to np, then there exists an NP intermediate language, that is a language in NP which is neither in P nor NP complete. And then you would have seen something called Oracle Turing machines. So an Oracle Turing machine is a Turing machine that has access to an oracle of some language A. So what is an oracle for a language A? You can think of it as a magical black box which decides A. So if you give that black box a string X, it would say whether X belongs to A or whether X does not belong to A. Okay. So an Oracle Turing machine is a Turing machine that has access to an oracle, and if the Turing machine is M, the oracle, the language whose oracle it has access to is A, then you would denote the Turing machine by M to the power A. And in particular, Oracle Turing machines have a special tape called the Oracle tape and three special states, QQuery, QYes and QNo. And how they function is the following. So when the Turing machine writes X on the Oracle tape and enters the QQuery state, in the very next step it enters the QYes state if X is in A and QNo state if X is not in A. So basically the oracle helps this Turing machine decide whether X is in A or not in unit time. And then you would have seen the definition of PH or the characterization of PH using Oracle Turing machines. So in particular, the class sigma I plus 1 is the same as the class NP to the Q set I, and the class pi I plus 1 is same as the class co NP to the Q set I. Here Q set I is the complete is like one of the complete languages for the class sigma I. Okay. So if you have no questions about this, then we can move on to the problems. Okay, so let's move on to the problems. The first problem is the following. Suppose 3 colorability is decidable in deterministic polynomial time. Then which of the following statements will certainly be correct? Select all the correct statements. The options are NL equals to P equals to sigma 2, GI, that is graph isomorphism, is in P, 3SAT is not in P, and there is a language in NP that is neither in P nor NP complete. So would you like to guess the answer to this question? Come on, this is an easy question. Okay, so there are two correct answers, P is equal to sigma 2 and GI in P, and let's see why. So we know that 3 colorability is NP complete, and so if 3 colorability is in P, that means P is equal to NP. Okay, and now we know that GI is also in NP, so if P is equal to NP, then GI is in P. So that tells us that this option is correct. Secondly, we also, if P is equal to NP, then the polynomial hierarchy collapses to the first level. Is this fine? You would have seen this in class.
Yeah.
Yeah. So if P equals to NP, then PH is equal to NP. Now we know that sigma 2 is contained in NP, right? Oh, sorry, we know that sigma 2 is contained in PH, so sigma 2 is contained in NP because PH has collapsed to NP, and NP is just P, so sigma 2 is in P. But we also know that NP is in sigma 2, so this gives us P is in sigma 2. So we have sigma 2 is in P, P is in sigma 2, and so P and sigma 2 are the same. So that tells us that this option is also correct. Okay, now let's look at the remaining 3 options. So the first option is NL is equal to P. The question asks us which of the following statements will certainly be correct. Now, as of now, according to our current understanding, we do not know whether P equals to NP or P not equals to NP would imply something for the NL versus P problem. So right now we cannot say that if P equals NP, then NL equals P. So this statement may be true, it may not be true, but right now we cannot say anything about it. On the other hand, for the statement for the option D, we can definitely say that 3SAT it should be in P. Why? Because 3 set is in NP, and if NP is equal to P, then 3 set has to be in P. So this option is definitely false, and similarly the last option is also definitely false. Why? Because if P equals to NP, then there cannot exist a language in NP which is not in P, right? So basically the second option is correct, the third option is correct. These two options are not correct, and we don't know anything about this. So the answer is B and C.
Sir, what can we say about the classes which are in I plus 1th class, sigma I plus 1?
Okay, yeah, so basically what we can say is the following. P is equal to NP is equal to PH, right? We saw this, right? Now PH is just this, union. Now, now pH is just this, k greater than or equals to 1 sigma I, right? So because pH is equal to P, we can also say that P contains sigma I for all I, but we also know that P is equal to NP is contained in sigma I. So this implies that P is equal to sigma I. So basically, even if you replace this 2 with any I, the option would still be correct. Does this answer your question?
Yes, sir.
Yeah. Okay, so the next problem is, it's sort of the complement of the first problem. Suppose 3 colorability is not decidable in deterministic polynomial time. Then which of the following statements will certainly be correct? And again we have to select all that apply. So option A is NL equals to P, P is equal to sigma 2, GI is not in P, 3 sat is in P, and there is a language in NP that is neither in P nor NP complete. So what's the answer to this one? Okay, so the answer is the last option, and the reason is the following. So 3 colorability is NP complete, so it is in NP. But the question says that 3 colorability is not in P, which means that P is not equal to NP, right? Now recall that Lardner's theorem says that if P is not equal to NP, then there exists an NP intermediate language, that is a language in NP which is not in P but also not NP complete. So Lardner's theorem immediately gives us the last option. There is a language in NP which is neither in P nor NP complete. Now let's look at the other options. Again, we don't know that if P not equals to NP, then NL not equals to P or NL equals to P. So right now we don't know of any connection between the P versus NP problem and the NL versus P problem. So we can't say anything about option A. Now option B is definitely false, because if P equals to sigma 2, then P must contain NP, but which would imply that P equals to NP, but 3 colorability is not decidable by a deterministic Turing machine, which means P not equals to NP, right? So the second option is definitely false. Now for the third option, we know that P not equals to NP and GI is a problem in NP, but that does not immediately imply that GI is not in P, right? Because it is as well possible that there is an efficient algorithm for GI but no efficient algorithm for 3 colorability, because as of now we don't know if GI is NP complete or not. So we can't say anything about this statement either. And if 3 sat, so this statement is definitely false, because if 3 sat is in P, and since 3 sat is NP complete, P would be equal to NP. So the only option remaining is this, and we saw that this is true.
Sir, yeah. I asked you for a list of the theorems last week.
Yeah, so okay, let me do one thing. I can copy those links in the chat at the end of the session.
Okay, sir.
Yeah. So let's look at the third problem. So the problem is that the following. Consider the following 2 statements. Statement P is that D space of n is strictly contained in D space n square root log n, and the second statement is D space n square is strictly contained in d space n square log n. Select the correct option. Only P is known to be correct. Only Q is known to be correct. Both P and Q are known to be correct, and neither of the statements is known to be correct. So would you like to guess the answer of this question?
Sir, B.
Was it B or D? I couldn't hear it properly.
B.
B. Okay.
B for both.
Okay. So okay, B is definitely correct, but so is A. So like both statements P and Q are correct, and the reason is the following. Over here we have D space, right? Not D time. And what do we know about the space hierarchy theorem? We know that D space of f of n is strictly contained in D space g of n if f of n is equal to small o of g of n, right? Now now n is small o of n log n, n square root log n, as well as log square n. So basically both of these functions over here satisfy the condition of the space hierarchy theorem, and so both statements are correct.
Okay, sir.
Yeah. The next problem is consider the following two statements. Statement P, L is not equals to NP. Statement Q, NP is not equals to P space. Select the correct option. Only P is known to be correct. Only Q is known to be correct. At least one of P and Q is known to be correct, and neither of the statements are known to be correct. So would you like to try this one? Okay, so the answer to this is yeah. Hello?
Sir, I think P might be correct.
D for Delhi or B for Bombay?
So D for Delhi.
Okay. Yeah, again, the answer to this one is C. And I sort of get why you said that D is correct. Because right now we don't know whether so right now both these problems, there are two problems. Whether L is equal to NP or not, or the L versus NP problem and the NP versus P space problem. So right now both these problems are open. So if I just gave you statement P or statement Q, then we don't know whether they are correct or not individually. However, what we do know is the following. We know that L is contained in NP and NP is contained in P space. Okay. But from the space hierarchy theorem, we also know that L is contained in P space. Why? Because L is this class. And P space is this class. In particular, P space contains D space n, and log n is equal to small o of n. Just a second, someone wants to join, I guess. Yeah. So P space contains D space n and log n is small o of n. So what we get from the space hierarchy theorem is that L is a strict subset of D space n, and therefore a strict subset of P space. Now suppose that both of these over equality. So suppose we had L equals to NP equals to P space. Okay, but then we would have L equals to P space, which we know is not true. So the statement that L is not equal to P space implies that at least one of these has to be strict, right? Because if neither of them were a strict inclusion, then you would have L equals NP equals P space. So which means that either L is not equal to NP or NP is not equal to P space, and so at least one of these is correct. Does this make sense?
Okay, sir.
Yeah.
Okay, sir. Yes, sir.
Yeah, so you were right. If I had just given you P and asked you whether it is correct or not, you would say you don't know. If I just gave you Q, you would also say don't know, you would be right. But it's that when you are given two together that you have a problem. So next problem is, consider the following two statements. Statement P, 3 colorable is reducible to the complement of 3 colorable by a polynomial time many 1 reductions, and statement Q, 3 colorability is reducible to the complement of 3 colorability by a polynomial time Turing reductions. So which of the statement is known to be correct? Only P is known to be correct, only Q is known to be correct, both P and Q are known to be correct, and neither of them is known to be correct. So what's the answer of this one?
Sir, I think Charlie C.
Okay, yeah. So the answer is B because of the following reason. So as 3 colorability is NP complete, statement P being true would imply NP is equal to co-NP. Why? Because 3 colorability is NP complete, so 3 colorability is in NP, so the complement of 3 colorability is in co-NP, right? So if 3 colorability reduces to its complement in polynomial time, you would have that 3 colorability and NP complete problem is in co-NP, and this would imply that NP is contained in co-NP. But then, as we have seen multiple times in, I think, the last couple of classes, this would also imply that co-NP is contained in NP, and therefore NP equals to co-NP. So if P is correct, then we would have NP equals to co-NP. Is this clear?
Okay, sir.
Yeah. But right now we don't know whether NP is equal to co-NP or not, right? It's an open problem. So we can't say anything about P. So that leaves us with statement Q. 3 colorability is reducible to the complement of 3 colorability via polynomial time Turing reductions. Here Turing is the key word. So what do we mean when we say that A reduces to B via polynomial time Turing reduction? It means that A is in P to the B. That is, there exists a deterministic Turing machine poly time M such that M to the B decides A, right? Now what we'll do is we'll construct a Turing machine M to the complement of 3 colorable, that is Turing machine M with oracle access to the complement of 3 colorability, which decides the 3 colorability language. Okay, so consider a machine M to the complement of 3 colorability that when given input a graph G simply queries the oracle of 3 colorability for G and outputs 1 if the oracle outputs 0 and vice versa. Then this machine decides 3 colorability. Is this clear? Why does this decide 3 colorability?
Yes, sir.
Yeah. So basically we have constructed a deterministic polytime Turing machine which, when given oracle access to the complement of 3 colorability, decides 3 colorability. So 3 colorability reduces to its complement via polynomial time Turing reductions, and so B is correct but A is not. So Q is correct but P is not. So that's the answer to this one.
Yes.
Yeah. So this is an interesting problem. Given an arbitrary legal possession of the standard chess pieces In a standard 8x8 chessboard, consider the problem of deciding if the white player has a winning strategy from the given possession. Which of the following statements most accurately reflects the complexity of the problem? This problem is decidable in constant time. This problem is NP complete. The problem is sigma 2 complete, and the problem is P space complete. Now before you guess the answer, this is a trick question. So would you like to guess what the answer is? Okay, so I think you might have seen in the class. Yeah. Hello?
Right. Yes, sir.
Yeah.
Sir, I think it's A.
Yeah. Yeah, you are right. The answer is A. So, okay, you would have seen in the class that the problem of deciding whether white player has a winning strategy on an n cross n chessboard is P-space complete, right? However, over here, the chessboard is just 8 cross 8. So the size of the chessboard is constant. So the number of possible chess positions starting from a given position is constant. And all you have to do is go through all of those positions and see if A has a winning strategy. So basically you have to go through a lot of positions, but the number of positions that you have to go through is constant. It's a huge constant, something like maybe 64 squares, 32 pieces, maybe something like 32 to the 64, but still it's a constant number.
Okay, sir.
Yeah. So the next problem is, suppose A is a language that is decidable in deterministic polynomial time. Then which of the following options is correct? The options are NP is strictly contained in NP to the A. Option B is NP to the A is strictly contained in NP. Option C is NP is equal to NP to the A. Option D is neither NP nor NP to the A is a subset of the other. And option E is cannot be determined from the information provided. So what's the answer to this question? Okay, so the
Is it E?
E. Okay, no, the answer is C. And the reason, okay, so if A were an arbitrary language, yeah, you can say E, but A is a language, it is decidable in deterministic polynomial time. That is, A is in P, right? So, okay. Now, first of all, NP is definitely contained in NP to the A, right? Why? Because you can just choose not to use the oracle at all. So, is this containment clear, NP in NP to the A?
Yeah. Yes.
Okay.
Yes.
So now what we need to show is this. NP to the A is in NP. And the reason, and here's how we can do it. So pick an L in NP to the A. There exists a non-deterministic NDTM which runs in poly time such that N to the A decides L. Okay, so what would N do? It would do some non-deterministic computation, and like throughout this computation it can query A, right? It can query the oracle of A, but A is in P, right? So what you can do is, whenever N queries A, you can simply invoke the polynomial time algorithm that solves A and return that solution, the solution of that algorithm as the answer of the oracle, right? So basically you can replace the oracle with a polynomial time algorithm So then n would be a non-deterministic Turing machine that calls a deterministic algorithm, a deterministic polynomial algorithm multiple times. So the overall running time of n to the a, or this modified n to the a, where you replace the oracle with the algorithm, is still polynomial. Right? So L can be decided by a non-deterministic Turing machine even without oracle access to a, and so L is in NP. And since this is true for every language in NP to the a, we have that NP to the a is in NP. Is this clear?
Yes, sir.
Yeah. So the next problem is, out of the given options, select all the classes that are contained in P space. P, NP, sigma 2 and pi 2. So there is nothing to explain in this question, it's a recall question. So what's the answer to this?
Maybe all are contained
Yeah,
in P
right.
space.
Yeah, so all of them are contained in P space. In fact, you can say something strong. Yeah. Basically, you can say something stronger because we know that sigma k and pi k are also contained in P space.
Yes.
Yeah. So the next question is also a recall question. In an Oracle Turing machine, the query to the Oracle is written into which of the following tapes? Input tape, work tape, query tape, or output tape? Yeah, so it's written to the query tape. This is just a recall question. There is nothing to explain over here. Yeah, so the next problem is, suppose that you are given a graph as an adjacency list. Then which of the following is the smallest complexity class that contains the 3 colorability language? The options are d space log of size of v. Here v is the vertex set of the graph. D space square root of log of size of v, D space size of v, D space size of log v, or D space size of log v, D space size of v square. So
Yes.
can you say that again?
A for alpha.
Okay, yeah. Okay, so the why do you think it is A?
Maybe we could solve it using the tree method.
Okay.
So the number.
Okay, okay. So how? Okay, what would you do in a tree method?
We could make other what you say tree where we could analyze all the steps, and at the end of the day we can make it out that it is 3 colorable or not.
Okay, but why do you think the size of this tree would be log size of v?
Because we might not be we should don't have to analyze all the edges. Maybe we have to just analyze what do we say, the upper half of the matrix. The lower half of the matrix would be as same as the upper half.
Okay, so even the upper half would be of like size order v square, right?
I don't know. Please.
Okay, so the answer is C, at least as of now, and the reason is the following. So every 3 coloring can be represented as a string sigma in this set 0, 1, 2 to the size of v, right? Is this clear? Is this clear why this is true?
Yes.
Yeah. So then what we have to do is just the following, right? If we go over all such strings and check if the string represents a valid coloring or not, we would be done, right? Now, since the number of strings is 3 to the size of v, we can go over all the colorings in order size of v space, right? Because every string is of size v, so we can basically write a string in order v space and check if it's valid or not, right? Now, so suppose we have written a string or a coloring v on our work tape. Now, how would we check whether this is correct or not, right? So to decide whether a coloring is valid or not, we'll do the following. We'll go to the adjacency list and check the following. For all nodes V in V, check to ensure that for all V in V such that U comma V is an edge, sigma U is not equal to sigma V. So we will go to the adjacency matrix, look up all the neighbors of V and make sure that U and V don't have the same color. Okay. Now what is the space requirement for this? This can be done using just the adjacency list from the input tape. We don't need to copy to the work tape. The coloring sigma on the work tape and a counter that counts up to size of V. So why do we need this counter? We need this counter because we are given input as an adjacency list, right? So when we are exploring the neighbors of V, it would tell us that a certain node is a neighbor of V, right? So basically the representation would be the following. This is the adjacency list entry for V. It would say something like node U1 is a neighbor of V, then node U2 is a neighbor of V, node U3 is a neighbor of V and so on, right? However, all of these nodes would be given to us as binary numbers, right? Basically denoting, so you can denote all the vertices as numbers in 0 to the 2. So this is your set V. And each of these vertices over here would be some number in this set, right? And that takes up, and you can write any number in this set using order log of size of V space. And then what you would do is you would initialize a, let us suppose that 10 is a neighbor of V, right? The 10th vertex is a neighbor of V. And what you would do is on the work tape you would initialize a counter to 10, go to sigma 1 and using this counter move to so I should start from 0. So basically you would initialize a counter to 10 on the work tape and use this counter to move to the 10th sigma 10, which is the 11th entry of sigma, and compare this with your vertex V, right? So in this way, using just a counter and the coloring, you can determine whether the coloring is right or not, and therefore decide whether the problem is 3 colorable or not. Whether the graph is 3 colorable or not. Is this fine?
Yes, sir.
Yeah. Okay, so the next question is related to this question. And so the question is, in the pad 3 colorability problem, so we are defining a new problem, pad 3 colorability, and the problem is defined as follows. One has to decide if a given graph is 3 colorable, but the input is a description of the graph followed by 3 to the size of v many hash symbols. So in the 3 colorability problem, the input is just the graph, right? Now after the graph you have a lot of these hashes. Okay, so the size of the input has increased like anything, where size of is the number of vertices in the graph. And which of the following is the smallest class that contains pad 3 colorability? The options are d times square root n, d times n log n, d times n square, and np. Here n is the size of the input, and over here notice that we have time, not space. So which of the following is correct?
Sir, n square time, because we have to give time to basically extract data from the given inputs.
Okay, so n is the size of the entire input, right?
Yes, sir.
So why do you think that extracting would require n square time? Okay, so here's a hint. Try to use the algorithm that we saw in the previous problem. Okay, so yeah, it's definitely in d time n square, that is true, but we can do something better. We can show that it's in d time n log n. Here's how. So as seen in the previous problem, we can decide 3 colorability by going over all possible colorings. Now what were we doing in the previous problem? We wrote down a coloring, then we went to the corresponding adjacency matrix, sorry, adjacency list representation, and basically went over the entire coloring and checked whether it was valid or not, right? So we have 3 to the size of v many colorings, and for each and every coloring we need to go over it once to check whether it's valid or not, right?
Sir.
Yeah. So pad 3 colorability is in d time size of v times 3 to the size of v. However, we are not asked whether it's in, so we are not asked its running time in terms of size of v, right? We are asked its running time in terms of n. Now n is the total input size. And what is the input? It is the graph plus 3 followed by 3 to the size of v many hashes, right? So the size of input n is 3 to the size of v plus the size of the graph. Now what's the smallest size of a graph? It is at least, the size of the graph is at least non-zero, right? So the smallest possible size of the graph is 0. The largest possible is order v square. So yeah, that should be order over here. So n is between 3 to the v and 3 to the v plus order v square. So n is theta 3 to the size of v, right? So we have that this is like n. So we are only left with this. But if n is equal to 3 to the size of v, then log n base 3 is equal to size of v, right? So size of v is theta log n. So this quantity over here is n log n. And so pad 3 colorability is in d time n log n. Is this fine?
Yeah.
Yeah. Okay, so let's move on to the next problem. So recall the generalized geography problem that you saw in class. It is a p-space complete problem, right? So suppose that generalized geography is decidable in deterministic polynomial time. That is, suppose that generalized geography is in P. Then which of the following statements can be inferred? The options are P equals to NP, L equals to NL, T space equals to sigma 2, and co-NL equals to P. So what's the answer to this question? Okay, so the question says that a p-space complete language is in P. Okay, so yeah. Hello? Yeah, I can't hear you. Yeah, I can just hear some background noise. I can't hear if you are answering the question or not. Okay, so the answers are A and C. P equals to NP and P space. Just a second. Either someone puts in the chat or. Oh, okay. Yeah. Okay, yeah, my voice broke, so let's go over the question again. Suppose generalized geography is decidable in deterministic polynomial time, then which of the following statements can be inferred? The options are P equals to NP, L equals to NL, P space equals to sigma 2, and co-NL equals to P. And the answers are A and C. Okay, so let's see why. So generalized geography is p-space complete, and the question tells us that it is in P. Now I claim that this means that P equals to P space. Why? For any language in L in P space, we can solve it in polynomial time as follows. First, we would reduce that language to the generalized geography language, and then we would solve the generalized geography instance in polynomial time, right? So basically, if we want to decide whether x is in L or not, what we do know is the following. There exists a polynomial time computable function f so that x is in L if and only if f of x is in generalized geography, and f is polynomial time computable. So what we'll do is the following. Given x, we would first compute f of x, and then since generalized geography can be is in P, we would check if f of x is in P, f of x is in generalized geography or not in polynomial time. And basically this would tell us whether x is in L or not in polynomial time. So every L in P space can be solved in polynomial time, and therefore P space is contained in P. So this gives us this. But we already know that P is, oh yeah, wait, no, this gives us this, but we already know that P is contained in P space. So this, both of these together give us that P equals to P space. Now what do we know? We know that sigma 2 is in P space. So P equals to P space implies that sigma 2 is in P, but as someone wants to join, yeah, okay, yeah.
Sir, I joined it from a different.
Okay, yeah, so where was that? Yeah, okay. So we have seen that P equals to P space, right? So now what are our options? P equals to NP and P space equal to sigma 2, right? Now we have P equals to P space, but we know that NP is contained in P space. So NP is contained in P, and therefore P equals to NP. So that's why this first option is correct. Now for option C, we know that sigma 2 is contained in P space. So if P equals to P space, sigma 2 is also in P. But we know that P is in sigma 2, so P is equal to sigma 2. So this option, is also correct. And like options B and D, like they might be correct, they might not be correct. But right now we don't know any relation between the P versus P space problem and the L versus NL problem, or the co-NL versus P problem. So is this fine?
Yes, sir.
Yeah. So in that case, let's move on to the next problem. So in the class, you would have seen NP complete problems, co-NP complete problems, sigma I complete problems, pi I complete problems. But did you see any PH complete problem? Or do you recall seeing any PH complete problem? Okay, so you wouldn't have seen any PH complete problem in class, and the reason is this problem. So the problem is as follows. A language L is said to be PH complete if L is in PH, and for every language L prime in PH, L prime reduces to L in polynomial time. Now suppose that there exists a PH complete language, then which of the following is true? PH collapses to some finite level, PH does not collapse to some finite level, or cannot be determined from the given information. Now this is an interesting question, so I would like you to guess, even if you might be, even if you are wrong, it would be good to guess answer to this question, because it's a very instructive problem.
I think PH will collapse.
Yeah, so yeah, A is the correct answer. And here's the reason. So what is PH? PH is a union of sigma k for k greater than or equals to 1, right? So PH is sigma 1 union sigma 2 union sigma 3 and so on. Now suppose that there exists a PH complete language L. Then L has to be in one of these sigma k's, right? So is this assertion fine? So if L is PH complete, L is in sigma k for some finite k. Is this assertion fine?
Yes,
Yeah.
sir.
Yeah. Okay. So now what does L being PH complete mean? It means that for every language L prime in PH, L prime reduces to L in polynomial time. Hence, every language L prime in PH is also in sigma k. Why? Because L is in sigma k. Is this fine?
Yeah.
Yeah. So what does that mean? That means that every language in PH is in sigma k, which means PH equals to sigma k. So the polynomial hierarchy collapses to the kth level. So the answer is A, and this is why you haven't seen any PH complete problem in class. Because right now the question of whether PH collapses or not is a big open problem.
Okay, sir.
Yeah.
So does that mean that any class, if it has a infinite hierarchy, then it cannot have a complete problem?
Okay, so it depends on how we define completeness, right? So for example, like, do you have any specific hierarchy in mind?
Not really, but
Right.
just a general class.
Yeah, so I think it would depend on what exactly the hierarchy is and what it means to be complete. For example, I can also, because of the, okay, so let me do it like this. So I can also define an infinite hierarchy inside NP. How? Like this. So I can say, what is NP? NP is equal to union over k greater than equals to 1 n time n to the k, right? So I have this infinite hierarchy inside NP. Why? Because okay, let me draw it. So over here I have n time n. Outside it I have n time n square. Outside it I have n time n cube and so on, right? So I can even define an infinite hierarchy inside NP, and then we have this usual notion of polynomial time reductions, right? But we know that NP complete languages do exist. So it would depend on the hierarchy and the reduction that you are looking at.
Okay.
Yeah. Okay, so the last problem is the following: true or false? For all A in L, that is for all languages A that are decidable in log space, such that A is not the empty language or the, there should be this typo over here, there should be a comma. So for every language A in L, so that A is not equal to the empty language or the universal language, and every B in NL, B reduces to A in polynomial time. Now before we look at what the answer to this is, or before you guess what the answer is, notice that if the question was this, then this is an open problem, right? Because if the question were this, then what it is saying is, does every language in NL reduce to a language in L in log space? So this is, if the question were this is just the NL versus L question, right? But over here the reduction is not log space, it's poly time. So the question is this true or not? So would you like to guess? Okay, so the answer is it's true, surprisingly. So basically if instead of P we had L, then this is the NL versus L question, and people believe that NL is not equal to L. So if this were L, then we believe that this statement is false, but we don't know a proof of it. However, if you change the L to P, then in fact we know that the statement is true. And the reason is the following. Fix any A in L so that A is not the empty set or the universal set. What we'll do is that we'll show how to reduce any B in NL to A in polynomial time, and we'll call this reduction function f. So we'll construct this f. Now the assumption that A is not equal to the empty set or the universal language is crucial for this step of the proof. So fix some y1 in A and y2 not in A. y1 and y2 are strings, and such strings exist because A is not the empty set or the universal language, right? Because if A were empty set, then y1 won't exist, and if A were the universal set, then y2 won't exist. So we are using the assumption that A is not equal to the empty set or the universal set to construct these y1 and y2. And once we have these y1 and y2, there is a very trivial polynomial time reduction. Here is the reduction. For any x in 0 comma 1 to the star, check if x is in B or not. And I claim that we can do this in poly size of x time. Why? Because B is in NL and LL is in P. So checking whether x is in B or not is easy if I give you polynomial time. So if x is in B, define f of x to be y1, and if x is not in B, define f of x to be y2. This is a very trivial reduction. So it is clear that x is in B if and only if f of x is in A, right? Because of the way we have defined x. If x is in B, then f of x is equal to y1 and y1 is in A. If x is not in B, then f of x is equal to y2 and y2 is not in A. So this statement is true. X is in B if and only if f of x is in A. Also, f can be computed in time poly size of x, right? Because what are we doing to compute f? Just checking if x is in B or not, which we can do in poly time, and if it is, outputting y1, otherwise outputting y2. So f is polynomial time computable. So what we have done is we have constructed a polynomial time computable function f such that x is in B if and only if f of x is in A. So we have shown that B reduces to A in poly time. Now notice that we did not use any special property of B, just that B is in NL. So this is true for any language in NL, and so any language in NL reduces to A in poly time, which is exactly what the question is asking, right? So the statement is true. So is this fine?
Yeah.
Yes, sir.
Yeah, so that's it for today. So if you have any questions, you can ask.
Could you please explain this idea of folding in TQBF completeness proof that we use?
Okay, so I think okay, I don't recall the exact term. So can you tell me what you mean by folded?
Actually, in the proof there is a recursion. So to reduce the so if we enumerate across all the paths, it would take exponential space.
Right.
So to reduce, actually, sir told we use this idea of folding.
Okay.
And yeah, so there actually pairs of configurations are used. So for all C1, C2. So, but
Yeah, okay.
I don't understand the idea of folding. What exactly it is? The general idea.
Okay, so can you see my screen? Or do I need to share? Yeah, okay.
Yes, yes.
Yeah, let me find some space. Yeah, okay, I have a lot of space over here. So are you asking this? Wait. So you have this configuration C start and this configuration C accept, right? And so the question that you are asking is in the context of finding a path from C start to C accept, right?
Yes, yes,
Yeah.
yes.
And so I think the normal way to do it is this, right? Exists T such that okay, let me do this. Path C start comma D comma 2 to the n minus 1 and path C, oh no, path D C accept 2 to the n minus 1. So for the sake of simplicity, I am assuming that the size of the graph is equal to 2 to Tn, okay? And so this is a normal way of doing it, right?
Yeah.
But the problem with this is the following, right? That so if you were to write, so now we want to figure out the size of this formula. By the way, path c star d to the n minus 1 means that there exists a path of length at most 2 to the n minus 1 from c star to d. Okay, so what we have basically done is space of 2 to the n is equal to 2 times space of 2 to the n minus 1 plus some constant, right? I don't care about the constant. So if you basically write down, like solve this recursion completely, you would get that s of 2 to the n is equal to order 2 to the n, but that is too large for us. That's the problem, right?
Yeah.
Yeah. And then what do we do? Yeah, I'm asking you, what do we do now?
Yeah. So there actually the concept of folding is used.
Right.
So instead of just configuration, so having a middle configuration, let us say M, so having a path from C1 to M
Right.
and then M to C2, so we use a pair of configurations, for example C1 C2.
Okay.
Now for all such pairs, if the pair C1 C2 is same as CM1, the first pair, then we check phi C1 C1 C2
Right.
in time t by 2. So but this concept I don't understand, how actually space usage reduces.
Okay. So here's the statement, right? For all C1 C2 okay, let me use D1 D2 because I've already used C. So the statement is this: for all D1 D2 C start is equal C start is equal to D1 and D2 is equal to D, or C except is equal to D2 and E is equal to D1 implies path D1 D2 2 to the n minus 1, right? So this is the statement, right?
Yeah.
Yeah. Okay, now here's why it helps. So this statement that I've written has two parts, this part and this part, right?
Yes.
Now notice that the only part that's going to blow up is this part, because I would recursively expand this part, right? The second part.
Yes.
And the size of the first part remains constant. Okay, so I have some statements like is equal to and or and some things like that, but you can always write all of this as a constant size formula, right?
Yeah.
Right, so you can convert this to a constant size Boolean formula. So now what is this recursion relation over here? It's s of 2 to the n is equal to s of 2 to the n minus 1 times, plus order 1, right? This is not small o, this is capital O. Plus capital O of 1, right? So if you notice the two recursions over, you would see that over here there was a 2, over here there is no 2. The reason is the following. Over here we were expanding this as well as this recursively, right?
Yeah.
But over here we have only one thing to expand recursively.
Yes.
Right, so that is why it helps.
Oh.
Basically,
Sir,
yeah. Hello.
please continue with this. I have another question.
Yeah.
Hello?
Yeah.
Can you hear me?
Yeah, I can hear you.
I said, please continue with this question. I had another question to ask.
Okay, yeah. So yeah, over here we have s2 to the n minus 1 and so on. So if you solve this, notice that this is reducing it, like this is reducing by a factor of 2 every time. So what you would get is like order n. Okay.
Yes.
Yeah. So basically the reason this is helping us is the following. We had two things to expand recursively, but we use these extra quantifiers to reduce that number to 1.
Okay.
Yeah.
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 Thank you.
Yeah. So
Uh,
yeah.
Sir, can you explain how matrix addition and multiplication both take log n time or log n space? Sorry.
Okay. So what is n over here?
N is the dimension of the matrix. The matrix is a square matrix.
Okay. So
Basically, it's square.
addition is simple, right?
Yes.
Okay. So it is very clear that addition is in order log n, right? Because what you do is, okay. So there. Okay. So okay. Let me write it. It would be easier that way. See if I can find some space. Yeah, I think I have some space over here. Okay. So suppose you are given matrices A and B, and you want to compute C is equal to A plus B. So Cij is equal to Aij plus Bij. Now what we'll do is the following. We'll have two counters. One counter for I, one counter for J. Okay. And these would go from 1 to n. And what we'll do, if the counter for I is, so suppose the values of these counters are I and J, then we would go to the I comma jth entry of A, copy that. Okay, we don't even need to copy that entry. We'll go to the I comma jth entry of A, find out its last bit, go to the I comma jth entry of B, find out its last bit, add these two bits, put the answer on the work tape, store the carry bit, and then go to the second last bit of A, second last bit of B, repeat this process, right? Sorry, second last bit of Aij, second last bit of Bij, repeat this process. So we would, for this we would need another counter, and the size of this counter would be basically the size of the log of the entries, bit complexity of the entries. So basically just using these three counters, we can add each and every entry of Aij and Bij. Is this fine?
Still, it's,
Can you repeat that? I didn't hear you properly.
Sir, does addition of two numbers take log n time?
Wait, is it time or space?
Oh, sorry, space.
Okay. No, so addition. Okay, so suppose you want to add two numbers which are given to you on a single tape, right? Then you would have to go back and forth between those two numbers, right? So suppose, I think we covered this last time. Suppose you have this bn minus 1, b0. Suppose these were on different tapes. Then you could simply just like go over both of these from right to left and add them in order one space, right?
Okay, sir.
But the problem is we are given A and B on the same tape. So suppose I want to find out what the kth bit of A is and what the kth bit of B is. I would need to go to the kth bit over here, right? So for that I would need a counter that counts up to k. That is why we need this counter, this third counter.
Oh, okay, sir.
Yeah. So basically, because of this, I can add each and every entry in order log n plus order bit complexity. Order log n plus order bit complexity of entries, right? So basically, because I can do this for every entry, I can do this. I can write down the entire matrix C on the output tape, right? So the complexity is this: order log n plus log of the bit complexity. However, that this is still order log of the size of the input, because bit complexities are also the input, right? Sorry. So okay, sorry. It's not log of bit complexity. It's bit complexity itself. Yeah, because if number is k bits long, right? Yeah. So basically, okay, no. So sorry. If a number is k bit long, then you need to go up to k. So yeah, it's log bit complexity. Yeah. Sorry, it's log bit complexity. And this is like order. This is still the order of n times bit complexity, but this size of the input would be n square bit times bit complexity, right? Or 2n square times bit complexity. So this is still order the size of the input, order log of the size of the input. So is it clear why addition is order log n?
Yes, sir. And in multiplication, maybe just that we have to multiply and then we have to add. So the space could be reused.
Can you see that again?
In multiplication,
Right.
we have to first multiply and then add multiple numbers.
Right.
So the space could be reused.
But to store
But,
current. Okay, so I want to. Okay, so if I want to multiply, if I want to find Cij, what is Cij? Cij is sum over L, AIL, BLJ, right?
Yes, sir.
Okay, so suppose this summation wasn't there. Okay, so what we'll do is the following. As usual, we would go to the, so we would compute C bitwise. So one strategy of computing C is the following. Compute AIL, BIL, sorry, AIL, BLJ, store it on your work tape and then add them up. But that would take up a lot of space, right? So what we'll rather do is the following. We would just pick, so we would be, okay, so we would compute C bitwise. So what we would do is, first of all, we would compute Cij 0. So by this notation, I mean the last bit of, the least significant bit of Cij. To do that, all we have to do is basically do all of this bitwise, right?
Sir.
I couldn't hear you.
Yes, sir.
Yeah, okay. So basically, I think if you do all of this bitwise, you will be able to do it in log n time.
Okay, sir.
Yeah.
It is true that it will take more time than addition. More space than addition. If
Maybe space in the absolute terms, yes, but not probably in the order. So maybe like for addition you might need like let's say 10 times log n space. For here you might need 20 times log n space. But I think the orders would be the same.
okay, sir.
Yeah.
Thank you.
Okay, and you also wanted the list of NP complete problems, right?
Yes, sir. Yes, sir.
Yeah. So I found two lists. Yeah. Let me copy the links. Yeah. So I put two links in the chat. Copy these to your local file or something, because I think after the meeting the chat would vanish. Yeah. So if there are no other questions,
Thanks, sir.
yeah. So if there are no other questions, we can end for today.
Thank you so much, sir.
Yeah.
Yes.
Thank you. Bye.
Thank you.